A dead star is collapsing, and there is no known reason it should be. White dwarfs are stellar corpses. When a star like our Sun exhausts its nuclear fuel, it sheds its outer layers, and the core that remains, compressed, dense, inert, becomes a white dwarf. No fusion, no outward pressure from burning. What holds it up is something else entirely, a quantum mechanical resistance called electron degeneracy pressure. Electrons at extreme compression resist being forced into the same quantum state. That resistance pushes back against gravity. The star is dead, but it is stable. Under normal conditions, it stays that way for longer than the current age of the universe. That stability has a limit. In 1930, Subrahmanyan Chandrasekhar calculated that if a white dwarf accumulates enough mass, approximately 1.4 times the mass of our Sun, electron degeneracy pressure can no longer hold. Gravity wins. The star collapses. This threshold is called the Chandrasekhar limit, and for decades it has been treated as one of the cleaner pieces of physics in astrophysics. A white dwarf approaches the limit. It collapses or it explodes. The process was considered understood in its broad architecture. What is observed does not always follow that architecture. Certain white dwarfs appear to detonate at masses inconsistent with the predicted threshold. Some explode well below 1.4 solar masses. Others appear to exceed it before collapsing. In specific cases, the density spike preceding collapse, the sharp increase in internal pressure that should serve as the final signal, arrives at the wrong moment, under the wrong conditions, in configurations the standard model does not cleanly account for. The observable pattern is not the anomaly. The anomaly is that the threshold itself appears to be unstable. A dead star is becoming unstable, not because something is happening to it from outside, from within. The mechanism that governs white dwarf collapse involves several interacting variables, and each one carries its own unresolved uncertainty. Electron degeneracy pressure is not purely a function of mass. It depends on the composition of the white dwarf, specifically the ratio of carbon to oxygen in the core, and on how that composition was established during the star's earlier life. Two white dwarfs at identical mass may carry different internal architectures, different thermal histories, different distributions of nuclear fuel. The Chandrasekhar limit assumes a uniform structure. Real white dwarfs are not uniform. When mass is added, typically through accretion from a binary companion, internal temperature rises. Thermonuclear reactions can begin before the mass threshold is reached. Whether those reactions trigger a detonation, a deflagration, or a controlled burn that stabilizes the star depends on exactly where in the core they ignite, at exactly what temperature, and in exactly what density regime. Current models can constrain this process statistically. They cannot predict it precisely for any individual event. The density spike before collapse should be traceable. It is not always. Observations of type Ia supernovae, the explosions white dwarfs produce when they cross the instability threshold, have been used as standard candles for measuring cosmic distances precisely because the explosions were assumed to produce consistent energy outputs. If the progenitor systems and ignition mechanisms vary, that consistency is not guaranteed. Some observed type Ia events deviate from expected luminosity in ways that do not map cleanly onto current models of white dwarf structure or mass distribution. The deviations are small. They are not small enough to ignore. A classification built on uniformity is facing evidence that the underlying system is not uniform. Mechanism breakdown mode requires following the chain from known system to failure point, and the chain in white dwarf collapse has a specific fracture. The known system, mass accumulates, internal pressure rises, threshold is crossed, collapse or explosion follows. The failure point is not at the threshold itself, it is in the ignition. Carbon detonation in the white dwarf core must be triggered by a compression wave reaching a specific temperature at a specific density. Whether that trigger fires as a detonation or a slower deflagration, a burn rather than an explosion, determines the energy yield, the remnant left behind, and the observable signature. Current physics does not have a first principles model that predicts from initial conditions which outcome occurs. The same set of starting conditions run through current models can produce different outcomes. Two leading frameworks have been developed to explain the ignition variability. The first is the single degenerate model. A white dwarf in a binary system slowly accretes material from a companion star, typically a red giant or main sequence star, donating mass through gravitational interaction. As mass builds, the white dwarf approaches the Chandrasekhar limit from below. Ignition occurs near the limit. The explosion follows. This model has a coherent physical logic and is consistent with a large fraction of observed type Ia events. Its limits become visible at the edges. Some type Ia supernovae occur in stellar environments where no suitable mass-donating companion has been identified. In certain cases, post-explosion searches for a surviving companion star, which should exist in the single degenerate scenario, find nothing. The absence is not definitive. Companions may be ejected at high velocity, may be difficult to detect, may have been consumed. But the absence recurs with enough frequency that a second framework gained traction. The double degenerate model proposes that two white dwarfs in a binary system lose orbital energy over time through gravitational wave emission, spiral inward, and eventually merge. The combined mass of the merger exceeds the Chandrasekhar limit, triggering collapse or explosion. No companion survives because both objects are destroyed in the merger. The model accounts for cases where no companion is found. It is consistent with the existence of white dwarf binary systems that are known to be inspiraling. Its limits are different. White dwarf mergers in many simulation scenarios do not cleanly detonate. The merger may instead produce an accretion-induced collapse, a neutron star rather than a supernova, or a subluminous explosion inconsistent with standard type Ia profiles. Producing the observed energy output of a type Ia supernova from a double degenerate merger requires specific conditions in the merger dynamics that models have difficulty reliably reproducing. The model explains the absence of companions. It introduces uncertainty in the energy output. Neither model closes the problem. Both remain active. There is a third layer below the ignition question, and it involves the white dwarf's internal structure at the moment of collapse. Carbon-oxygen white dwarfs are the standard assumed progenitor. Some observational evidence suggests oxygen-neon white dwarfs, a different compositional outcome from different stellar evolution pathways, may also contribute to the population. An oxygen-neon white dwarf collapsing under accretion does not detonate the same way. The electron capture reactions that dominate at high density proceed differently. The density spike preceding collapse has a different profile. If the progenitor population is compositionally mixed, the assumption of a single underlying mechanism is already incorrect. The observable pattern is a density spike before collapse. What drives that spike, and when exactly it arrives relative to the mass threshold, depends on internal structure that cannot be directly measured. White dwarf interiors are not accessible to observation. What is observed is the exterior, surface temperature, luminosity, the spectrum of light emitted. The interior, composition, thermal gradient, density distribution, is inferred from models and from the star's evolutionary history. When the interior deviates from model assumptions, the deviation does not announce itself until collapse. At that point, the observational window is milliseconds to seconds. The density spike is inferred from what the explosion looks like afterward. The mechanism that produced it cannot be rewound. There is a mass window around the Chandrasekhar limit where the outcome of collapse is genuinely uncertain. Not uncertain because data is missing, though data is missing, but uncertain because the physical processes involved interact in ways that produce sensitive dependence on initial conditions. Small differences in composition, thermal history, or accretion rate change the outcome. Models agree on the general architecture. They disagree on the specific trigger. Physics stops cleanly at the ignition boundary. What cannot be confirmed, the exact internal temperature at the moment carbon detonation begins. What cannot be directly measured, the composition gradient within the white dwarf core before collapse. What cannot be modeled deterministically from first principles, whether a given ignition event produces a full detonation a partial deflagration, or an accretion, induced collapse into a neutron star rather than a supernova. Each of these gaps is individually constrained. Together, they leave the collapse mechanism open. The use of Type Ia supernovae as cosmological distance measurements that contributed to the discovery of accelerating cosmic expansion and the inference of dark energy, rests on the assumption that the underlying mechanism is uniform enough to produce consistent energy outputs. If the progenitor population is mixed, if the ignition mechanism varies with composition, if the Chandrasekhar limit is not a clean threshold but a range with composition-dependent boundaries, then the standard candle assumption carries an unquantified systematic uncertainty. The question of how a white dwarf collapses is not isolated to stellar physics, where current models stop at the moment of ignition, in the interior of a dead star, in the milliseconds before it destroys itself. The density spike is observed in the explosion's aftermath. The process that produced it, the exact sequence of quantum mechanical failures, thermal runaway events, and pressure wave propagations inside a stellar remnant crossing a mass threshold, has not been confirmed from first principles for any single observed event. A dead star becomes unstable. The threshold is real. The mechanism remains unresolved.